Well, I'll start off with an introduction that I first met Pat in 1997 when I was visiting. At the time, it was the Renault team and called Formula 2000. And we started a partnership in 1998 and still running today. So 25 years. I think it's the longest running partnership in Renault.
Certainly in our history, yes.
In their history. So we're going to take you through 25 years of innovation that Pat's been involved with and try and do that in 20 minutes. So go ahead.
A lot of slides and a very short time to do it. Okay, so we bought our first SLA machine in 1998. We didn't really know what to do with it. Our ops director said, it looks cool, we better get one. So we bought one. He then shoved it down by the machine shop, gave the program inside of it to the CAM group, which I was in at the time doing 5-axis machining, and said, go and find something to make that with.
And this was your first application in exhaust?
That was right? Our first application, yeah. It was an array of exhausts for the wind tunnel model. The wind tunnel was a bit of a difficult nut to crack. The materials weren't quite ready for it, but we'll go through that later. So we bought this machine. What do you do? Well, everyone was doing function and fit because that was relatively easy, and we had lots of applications for that with fitting drivers into cars, making sure that they were comfortable, making sure they were happy with the instrument layout, albeit a very basic instrument layout, and making sure that things operated and worked as they should do prior to us cutting the metallic parts. So initially we were looking to find our mistakes really quickly, and we did.
I think it's interesting how much the steering wheel has changed in
It's changed a hell of a lot. Totally. That steering rack there in the middle photo at the bottom was a fully functioning steering rack. We made every single component and put them together, handed it to the design team, who went into an immediate panic and said, I've made a mistake, and had to run downstairs and stop the machine shop before they made the one cut that was about to scrap all of our steering racks for the season. So it was a very fortunate error that we found quite quickly.
And I think on this model you did form, fit, and function as well, but then also learned that the spanners don't always fit.
That's it. It looked right in CAD. It never applies more than to a Formula 1 car when you're trying to arrange it so the mechanic can get to every single fitting and fixing quickly. So it gained us a lot of knowledge, allowed us to design, iterate quickly at the request of the mechanic who would essentially be fitting the parts to the car on a race weekend. We'll crack on because it's a lot to do. So we started in 1998. We had a small number of machines, a little start off, got ourselves into it. It was quite quick. We figured out we need more of this and we need it faster. So our first SLA machine got chopped in and we upgraded that to 2 faster machines. Very quickly again realized that wasn't going to be enough. I had to expand it again. So we built ourselves a proper facility now. So rather than being in a room off the side of the machine shop and a programming office somewhere else, we actually built a dedicated facility for it and started to fill it up accordingly. As you can see, as the years went on, we added more and more kit. The applications changed a bit. So on the left there, you can see we were looking for flow analysis of our engine oil. That's a 2-cylinder engine, and the crankcase and sump oil flow we were looking to evaluate. Not bad when you watch the rev counter go up quite alarmingly, although in later years we went faster. The photos in the middle at the bottom is a coolant rig designed to check that the coolant was reaching all the parts it needed to, but also whilst the rig was moving to ensure that G-forces weren't having an adverse effect. And the same deal with the engine front face there with all the bearings intact. It was run at speed to ensure that the lubrication went to everywhere they needed to go. A Formula 1 car is quite an aggressive environment. When you're pulling 5G on a corner, your fluids don't tend to be where you think they're going to be. And fluid dynamics has moved on a long way now, but there's nothing quite like seeing it in front of you. We also did it with the engine rig, so that's our dyno test rig in France. There's about 7 of those. But we were running SLS intakes on the air, intakes, trumpets, various other bits and pieces around the engine where the temperature's allowed. And temperature has been a constant battle. So I said we looked at the wind tunnel, but it wasn't really what they wanted us to achieve. The materials at the time were quite brittle. If you left it on your desk for a couple of days, you were lucky if someone hadn't picked it up and broken it. And most of it absorbed moisture at quite an alarming rate. So blowing 150 mile an hour air over it wasn't necessarily a good thing.
Yeah, and I think one of the things that, one of the innovations actually was putting in these steel rods inside the stereolithography pieces to give them the rigidity they need for the wind tunnel.
So we did quite a lot of parts in the suspension areas, but we were quite limited to places that we could reinforce it with metallic work. And that was quite a problem for us. You can see the back end of the car there. There was engine cladding, there was gearbox shape, there was exhaust pipes. But we were really kind of limited to those sort of parts. A little bit in the cooling system, because we also airflow test the inside of the car as well as the outside of the car. But our applications were quite limited. It did allow us ever to start looking at ways of doing things slightly differently. So the image on the left is a radiator. It's made out of aluminium. It's an aluminium gauze with some micro tubes down the front of it with small holes in it to sense the pressure, air pressure flowing through the radiator. On the top, you can see all the hoses that would connect that to the sensing system for the wind tunnel model and provide the data to the aerodynamicists. Great, not particularly accurate. You couldn't always drill the hole in the right place. You weren't always sure the model maker fitted it in the right orientation, and the hoses often dropped off or got kinked as you were assembling the model. So we didn't really like that solution. So we found in SLA we could move all these channels inside the parts and connect them all together. So we now don't have many hoses. We have a central loom up the spine of the car, but everything else interlocks and the air passages through between part to part to part. So in the case of the radiator there, all those horrible tubes are gone. They're all built into the inside of the part, and on the very top there's a little manifold that connects everything together. Much better solution for us. Absolute accuracy. The aerodynamicist specs where he wants the hole, and that's where the hole is. So then we started looking at stiffer materials. And 3D Systems came along with a machine at the time called Optiform, and if anyone's seen one, I doubt anyone here has seen one, but it was kind of a cross between an SLS machine and an SLA machine in its construction. There was a bin of material at each end, a platform that went up and down in the middle, an ultraviolet laser on the top out of an SLA 7000, but the material was a really thick, heavy gloop. And if any of you have done your own body work on a car, Isopon P38 body filler is about the same consistency when it's wet as this stuff is when it's non-cured. However, it did prove the point that what we really needed was filled material to deal with the stiffness and the strength that we required for the wind tunnel. So there I'd built a pair of front wing end plates with all the flicks on it. We tested it in the wind tunnel. The wind tunnel were gloriously happy. However, getting your parts out of that gloop and putting the material back in the machine again was a little bit of a nightmare. And I still have nightmares about it. But it proved that concept. So with a bit of encouragement, the guys at 3D developed a similar style of material, but that would fit into an SLA machine. And we already had a few of these. So we were able to go from a material that was quite brittle and not particularly good in moisture, and I live in England and it's always raining, to a material that was very good with moisture, very strong, very stiff, very accurate, because the filler meant there was virtually no shrinkage. Our world exploded. So we filled 3 machines with that very, very quickly. Within 3 months, half of my competition had machines in their facilities with the same material, doing the same type of thing as we were doing to begin with. So it kind of took off in our industry. The number of parts we were able to do escalated from small, low-load components such as suspension and exhaust to rear diffusers, which is, if you know the architecture of a Formula One car, the funnel in the floor, if you like, at the trailing edge at the back is effectively sucking air out from under the floor, sucking the car down. The requirement for stiffness is quite high, but we were able to do these in that center section there. That middle photo is what we called the RCD, the rear central diffuser. I think we did 150 iterations of those that year, so that just the throughput became immense. At about the same time, we brought SLS into the system, and this encouraged us to put real parts on real cars and go racing, and there are examples down at the end of the room. We were able to make proper plastic bits, bolt them to cars, take them around a track, do 200 miles an hour, and they were still there at the end of it. Oh, fantastic. Suddenly, the world of the designer opened up, and he could come up with all sorts of weird, wonderful, wacky shapes, and we didn't have to have a guy making it for 3 weeks in composites. We could do it overnight in plastic. So the picture on the left is our electronics box. All the circuitry for the car was in there, and mounted underneath the side pod, or underneath the radiator duct inside the side pod of the car. It got a little bit warm. The electronics themselves generated some heat, and the radiator wasn't too far away, so we had to figure ways of cooling that. So the other ducts there are specifically for taking air from the surface of the car and bleeding them over the electronics. The differences in shapes, we have different ambient temperatures at different circuits, so we're looking to make the temperature correct, not as low as it can go. So if we were going to a hot climate, we'd add more air. If we're going to a cooler climate, we'd reduce the amount of air flowing over the part. We also got into investment casting quite heavily. The box on the left at the bottom there was done for us, thanks to John, by a company called...
that was Solidiform.
Solidiform, that's right, my memory's gone.
First people to cast sheet metal using stereolithography quick cast patterns. Quite a change.
So that box is less than 1 millimeter wall thickness all over. Quite intricate ribbing, very thin. He cast that, we mounted our electronics, and we'd got a box that could bleed temperature very easily, very quickly, saved us an awful lot of machining, and a really quick turnaround. But we weren't happy with just that. We wanted to go bigger and better than that. So we started looking at things like our gearbox main case. And again, if you know the architecture of a Formula One car, the gearbox is essentially part of the chassis. The rear suspension and the rear wing hang off of it. So it was taking 600 kilos of downforce from the rear wing and 900 horsepower from the wheels, or from the drivetrain through the drive shafts, and all the suspension float through that structure. SLA enabled us to make the patterns really quickly and amazingly accurate. So we were able to optimize our metallic structures, bring the wall thicknesses down, put the material where it needed to be, and take it away from where it didn't need to be, reducing our weight. So again, there are areas on that gearbox main case that are down to 1 millimeter. There are other areas that are significantly heavier because they took all the loads I was talking about earlier. We did find, however, we were able to produce those patterns within 1/4 millimeter in 2 days. Ship them out to the foundry. They would add the ceramic, pour the metal, send us the part back, we'd machine it. Amazingly quick turnaround for us is essential. We leave everything to the last minute. So being able to turn it around, move the lead time back a bit later in the season gave us the option to optimize the car a little bit further before we finalized the design. We moved on from that to bigger, stronger, better materials. That particular thing is a titanium gearbox main case. It's sitting in a booth down at the bottom of the room, the hall. It's in its pre-machined state, which it is there. It's 20 kilos of titanium. It actually took 2 builds on an SLA machine to make the pattern, and we stuck them together, and we were still holding 0.35 of a millimeter end to end on a 650 millimeter pattern. So the accuracy was really good. The wall thicknesses are really thin. and we were able to optimize those structures a bit further. It's quite a complex casting. We had to add on gating structures after that.
We've got about 5 minutes for 20 slides. So we'll have to pick up.
We'll have to pick up. Okay, so material development carried on. The next wind tunnel material there didn't settle out quite as fast as the previous one. Slight improvement in mechanical performance, slight improvement in build speed, but kept us ticking along. We kept having to expand our facility to add more machines, more throughput. That carried on right through to this year, where we added a new suite of machines. Our on-car applications have increased. We now do a lot more stuff on the race car, especially on the race car. There's around 300 additive components on our race car at any one time in polymers and metallics. There we go. Not everything's about the car. Market can get carried away from time to time and get me to do all weird and wonderful projects. They wanted a teapot. When we went to the turbo, they decided that it looked and sounded like a teapot. We did a custom Xbox there with a slice of gear ratio embedded into the box. That whole thing was 3D printed with the Xbox assembly put back inside it, so I had to reverse engineer it. They allowed us to do that. We then gave it away at a race. Got it. Metallic options came. We were able to do really lightweight structures. That's a small turning vane, but it's only got a 0.5 millimeter wall. There's a lattice structure inside that's just stiff enough to hold the skins. It didn't need to be structural. It's just there to move an airflow, but it needed to be really light. Then we get into more complex solutions. We were designing parts for our suspension. We needed essentially 1.5 meters of 5 millimeter hose, but we wanted to package it really conveniently. It needed to be in the right place. The car's doing 6G on the brakes and 4.5G around the corners. It had to be fixed and static, and it couldn't move. So we designed it, we validated the design work, we approached 3D Systems, and they printed it for us in titanium. Quite a difficult thing to do and to clean out, because there's 1.5 meters of tube there. To get all that powder out was quite tricky. And it being a hydraulic solution, we needed to ensure that there was no powder left inside it, because that would kill the units. So we went to CT scanning, we sliced every layer. We ensured that there were no debris, no small artifacts inside that could break free. And that became a standard application on our race car for a number of years. So you can see it on the left there's one on the front damper, and on the right there's one on the rear damper encased inside the gearbox. Unfortunately banned now, we're not allowed to do that anymore. It did allow us, however, to design, iterate at different tracks with different surface textures and bumps. We could change the shape and the size of the coils to increase or decrease the length, and essentially tune our suspension accordingly. Moving on, we do a lot on our exhaust system. That's Inconel part on the right, an Inconel part on the left, and the other 3 photos are of titanium tailpipe. The tailpipe was quite interesting. Our rear wing at the time had a single pylon holding the rear wing to the car. It wanted to go down to the middle, but that's also the position for the exhaust. So we needed a solution for the exhaust to wrap around the rear wing pylon. So it was made with a hole, slide it over the rear wing pylon, mount the rear wing, and connect it all together. The item on the left there is what we call the debris catcher. Our turbocharger is rather large, somewhat heavy by design deliberately. It needs to be kind of ballistic proof. And the FIA were a bit concerned that if the turbine wheel separated from the spindle, it would fire out the back of the car and potentially kill the driver behind. So we had to work out the containment device. So that fan-looking affair in there is really only to catch the turbine wheel if it separates from the turbine. On the right, there's some bracketry to help hold the pipes in the right place and hold them together. Then we started looking at figure 4, and they came along with this little tiny machine and said, how about having one of these? I looked at it and said, you're kidding, right? I've got all these huge SLA machines with all this fantastic material in it. I've got 3 SLS machines sitting up there I can do plastics with. what am I going to use this little tiny machine for that can only build something 70 mil by 120 millimeters? Well, it turned out how stupid an idea that was. Because it's absolutely fantastic. So if we want custom-made rubber parts, we can build an eggshell. There's a 36 cavity shell there. We can inject it with a polyurethane or a silicon of our choice. And when the cure time's over, we get the parts as we want them with a really good surface finish, really good accuracy in a really short time frame. And as I said before, in my world, that's quite important. So the rubber boot there was part of our brake system for the brake pedal. That's a 5-shore silicon. The part above it is a 35-shore silicon out of a mold generated in a couple of hours. So to us, a really, really slick way of doing things. I quite like a challenge. And so that particular part is to reconstruct a World War II Spitfire, a reconnaissance Spitfire unarmed. They were looking for a solution to add the rubber handle back onto the original metalwork. And someone put it on LinkedIn and they said, you could 3D print it. And they said, no, you can't. It has to be a steel mold tool. Well, challenge accepted. Just to prove I could, I said, I'll do that for you. Made a 2-part eggshell, put the metalwork inside it, closed it up, added the silicon, took it apart, and the metalwork is now encapsulated inside the silicon. Really, really nice demonstrator. I couldn't find anything at work to show the designers I could do it, so I took someone else's application and used that instead. When we started using mandrels for composite work, we have a challenge of moving fluids around the car. So we're given the engine, our engine team do that. That's set, there's nothing we can do to alter it. The next thing we design is the gearbox. Once that's designed, it's set, there's nothing we can do to alter it. We then throw an aerodynamic shape around it. That gets set, there's nothing we can do to alter it. Then we've got to make everything else fit. There's the challenge. So we have to take liquids from one side of the car to the other, from the engine to the radiator, from the oil coolers to the engine, and moving those fluids around in a well-constructed tube that wouldn't move and float around at 5 or 6 G was quite a challenge. Sometimes you have to change the cross-section from a round tube to a flat tube to get it through a gap and then back to a round tube again, but the size of the flow has to remain the same, so the aperture has to stay. SLA mandrels became great. So we can build that part in SLA, we can wrap it in carbon fiber, we can put it into the mold tool, close the mold tool, take it to our autoclave. The whole thing goes into a vacuum, pulls the carbon fiber against the tool, but the autoclave is also pressurized and heated. So the holes at the end allow the air pressure inside, and as the temperature goes up, it becomes elastic. So the air pressure is pushing the SLA against the carbon, and the carbon's being pushed against the tool. We end up with engineering surfaces on both the inside and the outside, and we can guarantee the consolidation of the material because we're squeezing it with pressure, and it's not a polythene bag, it's something with a bit more rigidity to it. So that works really well for us, and we use that quite a lot in our construction of our car. And there you can see a couple of the carbon pipes, the cross sections I was talking about, the changes. Pretty much impossible to make without additive manufacturing, I think. It's certainly within a composite world.
So we've got about 6 seconds for 6 slides.
6 seconds for 6 slides. Development continues. Have we got that many? I don't think we have. We helped with the development of the new SLA 750. It was designed with our input. The material was updated again to work with our PIV system in our wind tunnel, so we essentially shine really bright lasers at the wind tunnel model, pass a seed through the airflow, through the lasers, and track the seeds on high-velocity cameras, high-speed cameras. And we can basically see the CFD effect of swirling air in the wind tunnel. However, if you stick an old-style material in front of it, the whole thing illuminates like a big LED bulb. So that material was developed specifically to kill the UV, kill the light source from the laser. The machine there has now been upgraded to 2 lasers, so you can see there's 2 lasers drawing on the purple material at once. Massive speed increase for us, through parts of the tunnel faster, I should probably say I'm throwing about 600 parts into the wind tunnel a week, made in SLA, so it's quite a big volume of parts, up to 800 mil long. And the car's at the bottom of the room there, so come and have a look, see some of the parts we've made with the help of 3D, the materials.
Pat, you're going to be there in person to walk people through this.
I do occasionally, yes.
Yeah, so it's great to take a trip with Pat around the car and see all the innovations. Like you said, about 300 parts are racing on the cars every weekend, every race weekend. So we certainly appreciate the 25 years of an incredible partnership with Alpine F1. So just want
Been
to
an adventure.
Yeah, that it has. Any questions or anything we can take? Yes.
Just a quick question. In terms of your part selection for the car, of what to print, what to 3D print, what were your priorities? I mean, was it basically just, I don't know, maybe it was just performance-wise, or was it because it was maybe potential to maybe change and revolutionize the performance? I don't understand.
Some of each. So yes, we have a desire to iterate really quickly. Conventional tooling is long-winded in comparison. But I'm also kind of considered lastminute.com in the manufacturing of race cars. So if there's no time to make it, let's see what Pat can do in Additive. And I've literally received a design at 5 o'clock on a Friday, put it into a machine, taken it out of the machine at 6 o'clock on a Saturday, and driven it to the circuit to be fitted to the car for qualifying. You don't get to do that in any other business. It's really quite insane, but a lot of fun.
Thank you very much, gents. 25 years in 20 minutes was always going to be a challenge.
It was.
And so it proved.
Thank
you, John, for keeping chivying him along. Thank you very much
for the
insight.
All right.
And yeah, any questions, you can't miss them. You walk down the hall, there's a big race car there. Pat will be there. John will be there.
I will.
Thank you very much.
Thank you very much.
Thanks very much.
Appreciate it.
Thank you.